In this video, we're computing the limit of a sequence whose terms are given by 2n minus 1 factorial divided by 2n plus 2 factorial. And computing these types of limits actually turns out to be really important in the long run when we start testing convergence of series. So this is a really big trick that we're about to learn. Now remember, what we mean by the limit of a sequence is the limit as n grows to infinity of this expression that's generating the terms of the sequence. And the trick for these is to just start splitting factors off the factorial that's bigger. So just as a little side note here, I want to point something out about factorials. Just to keep it small and specific, let's consider 5 factorial. Remember, that's 5 times 4 times 3 times 2 times 1, where I obviously didn't have to write the times 1. Well, we could just gather the 4 times 3 times 2 times 1 and rewrite this as 5 times 4 factorial. And so we've split off the first term in a factorial. So this gives me the idea that what I can do with this denominator is start splitting off the leading terms until I end up with a remaining 2n minus 1 factorial, which will then cancel. So the first term in that factorial in the denominator is 2n plus 2. And then, of course, you multiply by 1 less than that, 2n plus 1. And 1 less than that, 2n. And what's left over is 2n minus 1 times 2n minus 2, and so on, all the way down to 1. In other words, there's our 2n minus 1 factorial. Again, the whole point of this is that the 2n minus 1 factorial is going to cancel now. And at this point, I would usually just allow my students to say that the result of this limit is obviously 0, because the denominator is growing to infinity while the numerator is staying constant. Now, it could be in your introductory calculus class that you're expected to actually expand that denominator into every single term and then divide by the highest power of n. That whole approach is predicated on the assumption that at some points, you've actually proven that the limit as n goes to infinity of 1 over n cubed is equal to 0 in some rigorous fashion. But in practice, in my experience, that proof never got done. So the following semi-formality is unnecessary in my opinion, but it may align with your experience in calculus. So what we're going to do next is expand this denominator. So I'm going to multiply the two binomials together first, and I end up with a 4n squared. And my cross terms are 2n and 4n. That gives me 6n, and my constant is a 2. And I still have to multiply it through by 2n. Now I want to get that denominator just written as a polynomial. So I'm going to distribute the 2n, and I get an 8n cubed down there, plus a 12n squared, plus a 4n. So now the usual semi-formal recipe is to divide the top and bottom by the highest power of n. That's going to give us a 1 over n cubed in that numerator. It gives us an 8 for the first term in the denominator, a 12 over n for the second term, and a 4 over n squared for the final term. Now again, this usually wasn't even proven rigorously, but we can say the limit as n goes to infinity of 1 over n cubed must be 0. So that's a 0. The limit of 12 over n is 0, and the limit of 4 over n squared is 0. So this reduces to 0 over 8, which again is 0. So as calculus teachers, we're always walking a fine line of semi-formality. But when I teach the course, I encourage my students to just stop right here. Just say that it's obvious if you see the denominator growing to infinity while the numerator stays constant, that the result is 0. Now, if you become a math major and find yourself in an upper division real analysis course, of course, you're going to be 100% logically rigorous, and there's a time and place for that. But as long as we're being semi-formal, we should be able to pick any method that works as long as it always works. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.